objectives of chapter 15 is to show you what is an what is electrostatics, what is an electric field, and how it's used to study the electric properties of matter and the environment surrounding it. So the main topics are going to be to introduce electric charge, insulators and conductors, Coulomb's law, and electric field. I'm pretty sure I'm gonna get to electric field today. We'll see. If not, we're gonna do it on Wednesday, electric field lines. So we're gonna cover all the materials needed for the lab on Thursday. So that's good. Okay, so many of you have done science in high school. So I'm hoping that you have done this experiment. If you haven't, I mean, basically what this shows you is how we observe static electricity. So pretty much what you do is you have pieces of paper on a table, and then you have a rod. It can be made of amber or plastic, it doesn't matter. And then you rub it with a piece of fur, like is shown here. And then what happens is that you can lift those pieces of paper because of attraction. That was the first sort of experiment or observation that we have that show us static electricity, which is basically the removing or the transferring of electrons from one material to another material. How? By rubbing the piece of fur on the rod of amber or plastic. So what you should know from physics and chemistry, right, is that the atom has a nucleus that has protons and neutrons, right, which is why it's the densest part of the atom. And then you have electrons sort of like orbiting the nucleus of the atom. Nowadays, we know that they're not really orbiting. They are in what we know as an electron cloud. But the first model, the Rutherford and then the Bohr model of the atom, they show the electron orbiting the nucleus, the positive nucleus, because they will model it as one proton and then one electron orbiting it. And why is that important? Because we use Coulomb's law and a bit of quantum mechanics, of course, to actually obtain what we know as the Bohr radius and the energy levels, which are the allowed positions for the electron to be due to levels of excitation, right? So when you study this before, or you have heard about electrons getting excited from one level to another, or doing an electron transfer, right? Or an electronic transition, sorry, from one level to another, that's basically due to an energy released or absorbed by the electron. But to model that, we actually use our physical laws, the understanding of how the electron actually orbits the nucleus of the atom. Now, of course, this only works for the hydrogen atom because there's only one electron and one proton. When we have more complicated atoms, like iron, for example, or carbon, it becomes more difficult. So that's when we start using the Schrodinger equation and all of these different models until we get to the concept of probability. But I digress, right? What you're seeing there is two situations that may arise in electrostatics. You may have repulsion or attraction. Like charges repel, opposite charges attract. That's the other observation that we have from static electricity. So that all comes into the concept of electric charge. So every object that you have and that is charged has a charge that is a multiple of the most basic unit of charge, which, as I showed you already, is a charge of the electron. The magnitude of the charge of the electron is given there, 1.60 times 10 to the negative 19 coulombs. Now, that is the magnitude of it. We know that for an electron, the electron has a negative charge and the proton has the same value, but positive. But whenever they tell you the magnitude of the charge, that's when we use the positive value of it, the magnitude per se. So we know that matter can be charged, and the charge of 4 coulombs gives you, or with a value of the charge that an object may have, you can estimate the amount of electrons or the excess of electrons or protons an anion may have, right? And this is what I was talking about, right? The electrons are in an atom as a cloud surrounding the nucleus. The cloud is negatively charged, and the nucleus can be positively charged if there is an excess of protons. Now, the neutron doesn't have any charge, so it doesn't play into account for this. So then you're probably wondering, well, you have electrons and you have protons, so are they orbiting like planets around the sun? Sort of. That's why this was called, at the beginning of the 20th century, when this was all studied, this was known as the solar system model. And the reason why it stuck for a while is because it was a very simple, elegant, and it resembled what we knew about the universe. However, nowadays we know that just like with the solar system, the orbits per se of the electrons around the positive nucleus are not circles, but are more orbital ellipses. And they're not really orbits. They are just a cloud of electrons surrounding the nucleus of the atom. All right. And what's true, however, are the whole concept of energy levels. That's actually all right. That's correct. But we don't know exactly where the electron will be, as you know from the uncertainty principle, right? The Heisenberg uncertainty principle. So the idea behind this is that electrons are less massive and are normally free to move, especially in a conductor. The main difference between a conductor and an insulator, for example, plastic and iron, right, is that electrons in iron or copper or gold are free to move on the surface. So when you heat up or when you charge a conductor, all the charge stays on the surface, thanks to those free electrons. So if you were to remove charge per se from one object to another, like what happens when you wrap the amber rod with a fer, you are removing electrons or you are transferring electrons into the bar. So what happens if you transfer electrons into the bar? The bar has an excess of electrons, so it becomes negatively charged. If you remove electrons from the bar, then it's the opposite. You are removing electrons, so you are positively charging. So you are charging by conduction. See what I mean? Now, this has been replicated in the lab, of course, and the basic example is the pieces of paper with the wrapping of plastic. So if you have a positive charge and a negative charge, they will attract. That's how we know the experiment works. But all that is static electricity. We're just removing and transferring electrons. We still are not talking about electrons moving, like for example in a cathode ray tube. Not yet. We're going to get into that later. So those are important observations that we did to understand the whole concept of charge. And there you are, right? If you transfer electrons towards the amber rod and you remove them from the fer, that's what happens. Now, what about the overall charge? Well, you probably remember about conservation of mass and conservation of energy. You can neither destroy or create energy or matter. You can only transform it. The same is with charge. You cannot create or destroy charge in the universe. It can only be transferred from one object to another. So if the amber rod and the fer were neutral, then the addition of the negative charge and the positive charge of both objects after rubbing them will be 0 coulombs as well. That's the conservation of charge. All right. All right, I spoke about this already. And then, of course, we have the whole idea of polarization. As I was saying, right, matter is made of atoms, and in the atom, we find the nucleus and the electron cloud. So can we polarize materials by using a charged rod? Yes, basically you are seeing it there. If you have a positively charged rod made of any material, and you place it nearby the environment of a sphere, it can be conductive, it can be an insulator. Then you will see that the atoms are distorted, where the positive charge will be pushed away from it, and the negative will be pulled towards a positive charge rod. And then later on, we can use this to charge objects by induction without the using of contact, direct contact or conduction. All right. A conductor has electrons free to move in the surface of the conductor. This explains why during winter, when you touch metal, for example, the door handle, the doorknob, to open a room, you may get a discharge. Or when you touch your friend's sweater, you also get a discharge. Because as you move in a dry environment, because that's what happens on winter, right? Sometimes you will notice that it becomes very dry. Then electrons or you can easily charge objects in the environment. And when you touch it, since we also carry our own electricity, remember synapses, right? From bio, you can get charged, and depending on the type of contact, right? Meaning on the surface, it can actually hurt. Which is why I always recommend people, before you touch metal during winter, you wanna rub against an insulator. So what I do when I open the door, you wanna rub your hand on the wooden frame of the door, so you remove any excess of charge in your hands or body, and then you can easily open the door. All right. An insulator, however, is a material where the electrons are moving from atom to atom. And the thing is that they are all, in terms of distribution, they are distributed in the whole volume of the object. What do I mean by that? Imagine this is a conductor, right? So the plastic, imagine this was metal. If this was to be charged, or maybe this better, right? All the charge will be on the surface of this conductor. But if this is an insulator, this is an insulator, the charge will be the liquid. You see, the charge is distributed all among its volume, which is why the way electrons move is much more slowly than in a conductor. Okay, those are the main differences between insulators and conductors. Sort of what you probably discussed when you talk about conducting heat, right? The reason why metal conducts heat better than an insulator is because of the free electrons on the surface. Or as we say in chemistry, the free electrons in the outer shell. There are also semiconductors, which basically have properties in between a conductor and an insulator. All right. This can be changed with their chemical composition. We're not going to be talking too much about this, but in circuits, sometimes it's useful to have semiconductors.
It's better. Try it out next time you park and rush to them.
What was that? Okay, so these are all the overall properties that we observe when we study static electricity: conductors, insulators, attraction, repulsion, charging an object. But how do we quantify all this? We quantify all this by introducing Coulomb's law. So I want to leave that in there, and let's explore this equation a little bit, and then we'll do some examples of it. So Coulomb's law gives you the value of the force between 2 point charges. Now, if you have studied Newton's gravitational law or law of gravity, that equation looks very similar, right? The force of attraction between the Earth and the Moon, or the Earth and the Sun, is modeled by a very similar equation. But the difference is that instead of charge, we use the masses of the planets, and instead of K, we use the gravitational constant. In Coulomb's law, we have that the electric force or electrostatic force is equal to K times the magnitude of Q1, the magnitude of Q2, divided by R squared, where R is the distance between Q1 and Q2. Units-wise, Q1 and Q2 have to be in coulombs, and R has to be in meters. What about K though? K is a constant. Now, in the book, they give you this as K. However, I'm gonna let you guys approximate this as 9 times 10 to the 9 to make it easy for the problems. And those are the units for the Coulomb constant. Newtons meter square per Coulomb square. So this force is a vector because you may have magnitude of the force, but also direction, depending on how the charges are placed or where they are placed. The force is along the line connecting the charges. It can be attractive or it can be repulsive. Now, if you have two charges, you may have these situations. They repel, they attract, or they repel if they are both negative, positive, negative to positive. But you may have multiple charges. So let's do an example that is similar to, you're kidding me. Let's show you a problem that is like this: 3, 2, and 1. Basically, problems where you have to use Coulomb's law. All right. What I'm gonna do is, first, we're gonna do problems in 1 dimension, like this. And then we will do problems in 2 dimensions before we introduce electric fields. All right. So when I do the problem, if you have any questions, please feel free to ask. All right. So that's good there. All right. So to use Coulomb's law, you have to make sure that you are careful with the units, with the signs. You need to be careful, you need to be comfortable with vectors. A few things, by the way. Since we're talking about point charges, we are going to be using a lot of prefixes because we're dealing with very small numbers. Look at the charge of the electron, right? So since we're dealing with small numbers, right? We're going to be using micro and nano most of the times to list the value of the charge of an object. I can give you a charge, and I can say that this Q is equal to 6 nanocoulombs. But we need to have this in coulombs. So you need to remember, or you need to change that into coulombs. 6 nanocoulombs is basically 6 times 10 to a negative 9 coulombs. Right? I can also give another charge, Q prime, and I can say that's equal to 20 micro coulombs. Micro is 10 to a negative 6. So we just say that that's equal to 20 times 10 to a negative 6 columns. All right. So just keep in mind that in the textbook, in exams, and in the class, we're going to be using prefixes like that. All right. Okay. So let's give you an example on how to do a few of those problems of columns. So example 1. On the x-axis, you're going to be given 3 charges. 1 there, 1 here, and 1 here. The value of the charges are going to be given like this. 4 nanocolumns (10 nanocolumns) and negative 5 nanocolumns. See that, right? Yeah. Positive, positive, negative. And then I'm going to give you some distances. So let's say this distance is of 60 centimeters, 60 centimeters. And then this is 30 centimeters. No, 30, 20. The question you can be asked is find the charge, find the force, find the electric force vector at 10 nanocoulombs. So what is the force acting on this charge? All right. So we have to use the equation force equals to K Q1 Q2 over R squared. That's the electrostatic force. Now, R has to be in meters. Q1 and Q2 have to be in coulombs. And we know that K, I'm going to use 9 times 10 to the 9 Newton meter square over coulombs. And the values of the charge are in half, so I'm just going to use the magnitude of the charges. But we have to be careful though, because the electric force is a vector. So with the first step, when you do a problem like this, you want to draw the direction of the force. How? Between 10 and negative 5. Because this is negative and this is positive. They are going to attract. So this is my reference charge. So this charge is going to be like this towards 5. Because that's positive, that's negative. And I label this F1. Make sense? Right? What about 10 and 4? What about 10 and 4? They both are positive. Because they are both positive, they repel. So they are going to repel. So you're going to have a force here. Here. F2. Why do you need to do that? Because now you can see there in the screen, on the screen, that F1 and F2 are going on the same direction towards the positive x-axis, towards the east. That means that you are going to add them. You draw the direction so you know whether you have to add or subtract, like we did with the vectors at the beginning of class. So you have to add F1 and F2. So now the next step is to find F1 and F2. So let's find it. How do I find F1? F1 is between 10 and -5, but hey, absolute values, right? So F1 is K, that's K, Q1 times 10 nanocolumns times Q2 absolute value of -5, which is 5 nanocolumns, 5 times 10 to the -9. Divided by the distance squared. And what's the distance? 20 centimeters. Hey, that's 20 centimeters. 20 centimeters has to be changed into meters. 20 centimeters into meters, there is 100 centimeters in 1 meter. That means that 20 centimeters is 0.2 meters. Make sure you have that written down as well, okay? Your conversion between centimeters, millimeters, meters, also kilometers, that sometimes will show up. So 20 centimeters will be 0.2 meters squared. Make sense? Right? See the equation there? So this is what I was talking about. You have powers of 10. Well, 10 to the 9 with 10 to the -9 can be dropped by law of exponents. 50, 5 times 10 is 50, plus 9 is 450. So that will give me 450 times 10 to the -9. And 0.2 squared is 0.04. So now I just have to do that. So I reduce the expression. So 450 divided by 0.04, that gives me 112.5. So I get 112.5 times 10 to the -9 newtons. Like that. That's F1. Right? But I still need to find F2. Once I find F2, I can add it with this and find my net force. So for F2, what we're gonna do it here. Here, F2 is the same equation, 9 times 10 to the 9. Now F2 is between 10 and 4. So I have to do 10 times 10 to the -9, 4 times 10 to the -9, divided by the distance. Now the distance is 60. What's 60 centimeters in meters? 0.6. So that will be 0.6 squared. Right? Now, I will just simplify this like that. 4 times 10 is 40, times 9 is 360. So 360 times 10 to the -9 divided by 0.6 squared is 0.36. 100 10 to the 4. So that gives me 10, 1,000. So 1,000 times 10 to the -9. No. 40, 9, 60, 50, 450.
Hey, Professor, for
Yeah.
for F1, would it not be 112.5 to 10 times 10 to the power of -7?
Yeah, yeah. That's right. So that's this 1, 1, 2, 50. 1, 2, 3. So, okay, this is 10 to the -6. Which is the same exponent here. Times 1,000, 1, 2, 3. So 11 point. This is 11.25 times 10 to the -6. All right. Thanks. That's the answer. So I made the calculator there, I didn't see it properly. That's the force value for F1, that's F2. Why do I do it like that? Because I have 10 to the -6, 10 to the -6. That's F2 also going to the right. Both are going to the right, as shown in the picture. Now you just have to add them. If you were to add them, here, F1 and F2, this number plus this number will give you 12.25 times 10 to the -6 newtons. That's the force at 10 nanocoulombs. Vector-wise, as a vector, it will be 12.25 times 10 to the -6 I newtons. That will be your final answer for that question. Okay. Now, you see, I use the equation twice because there are 3 charges. And I look at the force acting on 10 nanocoulombs, right? So, I don't know if you guys have any questions regarding this. So at the end of the day, once you understand how to use the equation and drawing those vectors there, the rest is just your math. As you can see, F1 and F2. Be careful with the prefixes, be careful with the directions at the end. Now, in the assignment as well, they ask you to find the force on every other charge. So let's do one more. Let's find the force acting on on 4. Let's check what's the value of the force acting on 4 nanocoulombs there. All right. Let's see. So what's the force acting here? The same equation as basically the same method, but we have to be careful with the directions. So between 4 and 10 nanocoulombs, since they are both positive, they repel. And guess what? Look, if you look over there, here, this is the force acting between 10 and 4 nanocoulombs. By Newton's third law, for every action, there is an equal and opposite reaction. So the magnitude of the force that I found over there is the same force that the charge of 4 nanocoulombs is experiencing. You see this F2? This could be also, let's call it F3. They are not the same vector, but they have the same magnitude. Vectors may have the same magnitude, but different directions, different vectors. So F3, the magnitude of F3 though, I found it, is that 10 to a negative 6 newtons. Because it's the force between 10 and 4. That makes sense, right? But is that the only force acting here? No. There is 4 nanocolumns and also negative 5. But they are opposite charges, positive and negative. So they attract. So there is a force of attraction here. Let's call it F4. So we need to find the magnitude of F4. F4 is the force due to 4 and negative 5 at a distance of 80 centimeters, 20 plus 60. So here it will be K 4, 5 over 80 centimeters, which is 0.8. Any questions about that? I don't think so, right? I mean, it's the same. Now we have to be careful with this. 4 times 5 is 20, times 9 is 180. Times 10 to a negative 9 over 0.64. All right, so let's double check this, be careful with this. So we have 180 over 281.25. Times 10 to a negative 9 newtons. That's my force between this and that. But F4 is going to the right. F3 is going to the left. So we need to subtract the values between these ones and these ones here. This minus that. So that's 10 to a negative 6. Let's use some math, okay? Because how do you subtract that value with that value there? That's 10 to a negative 6 newtons. That's 281.25 times 10 to a negative 9. So I'm going to take that number and I'm going to change the 10 to a negative 9 to 10 to a negative 6. How? How do you change this to 10 to a negative 6? This is a very important math trick. All right? Basically what you do is you multiply this by 1,000. If you multiply this by 1,000, that's 10 to a negative 6. But then you have to divide this number by 1,000. So the number doesn't change. So this number is basically 0.28 times 10 to a negative 6 into 6 fixer. Now I can subtract this minus that. Because if you think about it, this is like 1 times 10 to a negative 6, right? How about that? This is that 1.0, and then that's that. So this is going to the left, that's going to the right. So there is more force going to the left than to the right. because that's 1, that's 0.28. So what you write here, is that's positive plus the negative of that. How about that? That will be your addition of those vectors. That will give you 0.72. Negative 0.72 times 10 to a negative 6 newtons, or magnitude wise, or sorry, vector wise, we'll have to do it on the x-axis. You can leave it like that, or negative 0.72 times 10 to a negative 6, or negative I newtons. Or you can say towards the west. Both are right. All right. But that's how you use columns though. When the charges are on one axis, on one dimension only. Any questions about this? That's an important concept. That's basically what you're gonna have to do at the beginning. The main difference between the examples here and the WebAssign are the numbers. So be careful with the numbers they give you. They're gonna give you the same sort of units in terms of centimeters, micro or nano columns, all right? And I also noticed that there is a problem here. Normally the WebAssigns, I normally group them. So the first group from assignment 1 to assignment 5 or 6 are due near the end of July. Yeah, near the end of July will probably be due. The 26, 27, to give you time to study also for the exams. Now, that's for later. Are there any questions? All right. So let's talk about electric field. All right, and then with electric field, I will introduce forces and fields in 2 dimensions. All right. So what you saw today, or what you've seen so far, is how to point charges, because these are point charges, are acting when they are placed on a given situation or in a given arrangement, and how they interact with one another. Now, the concept of force is important, but where does this force come from? Why do they attract or repel? And why do they have those values, right? To understand that and to understand the motion of a charge, which is one of the objectives of this chapter, we need to introduce the idea of electric field. So let's show you what is the electric field. In the textbook, they label electric field like this. So you have electric field. And it's labeled as E vector equals to force electrostatic divided by a test charge Q. So the electric field is the value of the force per unit charge. The force is in newtons, the charge is in coulombs, which gives you an overall unit for electric field of newtons per coulomb. Now, the electric field is a vector, and it's a very important quantity, a physical quantity that we use to study the environment in which a charge may or may not move. Let's suppose I give you a charge here. And the charge is moving to the right. If the charge is moving to the right, there has to be a net force pushing it. Why? Because we know that the net force acting on a body or in a particle is equal to mass times acceleration. So this charge may be accelerated towards the east. Now, in mechanics, you study the idea of the force of gravity, friction, and so on. But if I give you a charge in an empty environment, in vacuum, for example, then the whole concept of friction is unneeded. Now, what about the force of gravity? Well, something that you should know, and please make sure you write this down, is that the mass of the electron is equal to 9.11 times 10 to a negative 31 kilograms. Furthermore, the mass of the proton is equal to 1.67 times 10 to a negative 27 kilograms. So what's the value of the force of gravity? mg. And do you think gravity will play a huge role? No. Gravity is actually the weakest of the fundamental forces of nature. So the electrostatic force, which later will be joined with the magnetic force to create what we know as the electromagnetic force, is actually more powerful, it's stronger. So if you have a charge in an environment, like here in a room, moving to the right, then the net force will be the electric force. That means that the electric force, this, is pushing the charge to the right. So if the acceleration is to the right, the force has to be to the right. Now, what do we see in this equation? We can rewrite this equation as the electric force vector equal to the electric field vector times the charge. Very important. What this is telling you is that the electric force, now we can find it by using the electric field. So the electric field and the force are parallel. If the charge, this is the thing now, this charge Q has to be positive. The test charge is always positive. So if we use that and that, then I can easily tell that the electric field is also going to the right. See what I mean? We know already from what we did before that there needs to be a charge with another charge to give you Coulomb's law, which is electrostatic force. Now what we are saying is that instead of worrying about the charge or the interaction between charges, I can just look at the interaction between the charge and the electric field. Now, who produces the electric field? Well, it's a source, and the source can be very far from this. So if I have the source charge here, as we go farther from the source, the electric field will get weaker. We are going to introduce the equation for electric field in a minute. For now, I want you guys to see the concept of it. You know what you can actually relate this to? Gravity. As a spaceship moves away from the Earth or from a body with a gravitational field, with gravity, the value of gravity, the value of the gravitational force becomes weaker to the point where that's why as we go in outer space, astronauts are floating, right? Because the value of gravity gets weaker and weaker. In the case of an electric field, it's the same. As we move farther from the source, the electric field becomes weaker. Now, I have that equation for electric field. Can I find an equation for the electric field due to a point charge? Well, yes, you can. We know that the electric force is equal to electric field times the test charge. Well, what's the value of the electric field by the source charge? The source charge is on the left and is given this electric field. Well, we know that the electric force is equal to K, the source charge, the test charge, divided by some distance squared between these two. But wait a second though. That's equal to E coulomb. The magnitude of E we can cancel Q's. And there you are. The electric field, the equation for electric field due to a point charge is KQ over R squared. Newtons per coulombs are the units. There. But that's the equation, and then I show you how the electric field works. What about what I showed you at the beginning of class with electric field lines? Well, that's the idea behind electric field. Electric field allows you to study the environment by understanding how a positive and also a negative charge emit electric fields. Let's use point charges for now. Let's use a positive point charge. So if I have positive Q, how do I emit or how do I draw the electric field lines due to that point charge? When it's a positive charge, the electric fields are radially outwards. So they emit fields like this. If the charge is negative, right, then no, they don't absorb, but the electric fields are towards the charge. That's important when you are going to compute the electric field on a given region. All right. So the idea with mapping electric fields is to study the interaction between a positive and a negative charge, or also a positive and a positive charge. One of the most common examples that we use a lot in experiments and also in real life is a parallel plate. So here's where we get into more, when we get into more realistic scenarios. A parallel plate capacitor, as we call it, right, is a device that has two conducting plates. Now, they are in 3 dimensions. I'm gonna project it on the board, and then you're gonna see also, you're only gonna see this. The thing is that one conducting plate is positive and the other one is negative. What we observe when we do the experiments on this is that the electric field always goes from positive to negative. That's an important property of electric fields. Electric field always goes from positive to negative, like this. Now, why does it go in this direction? Well, because as you probably have seen already, or you're gonna see this week, the way we trace electric fields is by using what we know as equipotential surfaces or equipotential lines, which are lines with the same potential difference. What's potential difference? Well, if you have used batteries at home, then you know that you have 1.5 AA batteries. That 1.5 is 1.5 volts. That volt is the potential value of an object. Okay, that's gonna be more a topic of chapter 16. But just to show you here, the equipotential surface or line for this guy will be this. And what we have is that they make 90 degrees with electric field lines. So that's a situation that we have. The main thing that I want you guys to take from this is that the electric field goes from positive or negative, and that we can trace electric field lines between positive charges and negative charges, depending on the geometry we give it. So how about 2-point charges? Can we also do that? Yes. We can analyze the electric field lines between a positive and a negative charge. Now, you are going to do this also in the lab, but in the book, they show you this, and we know that the electric field lines go away from this and they go into this. So look at this. There you are. These arrows are important because they're telling you that the electric field is leaving positive Q and entering negative Q. Furthermore, we have 6 lines entering negative Q, and we have 6 lines leaving positive Q. Why they are the same amount of lines? Because they both have the same magnitude of charge. If the positive charge was double, the negative charge, there will be twice the amount of lines leaving than entering the negative charge. So you will have 12 here, I don't know, 6. There is a problem like that in the assignment, so make sure that you are paying attention to this. Now, how do I know they look like this? Well, as I said over there, equipotential surfaces. Using a voltmeter in the lab, we can trace the electric field lines. One in the middle happens to be completely vertical. But then as we go to the right or to the left, this is what we find. We find that they become circular. And that if I draw a tangent line here, this tangent is the direction of the field. which makes a perfect 90-degree angle with an equipotential surface. I don't know if you can see there. Yes, you can. You see that? The same here, right? So that is how we investigate electric field lines. And this is why this is important. This gives you a better insight of how static electricity and how charges may move or may not move, which now brings me into another example, right? Can we use this in sort of an example? How can we use it in examples? Well, electric fields are used in different devices like the parallel plate to accelerate charges in motion, right? Or to stop them. So, yeah, we have time. So I want to do one example first with a charge in equilibrium. Now, how can you make a charge in equilibrium? We did a Coulomb's law today, and you can do it by having two or more charges. But if you have one charge, one object with given mass, can that object be suspended above the ground? Yes, you can use magnetic forces, which we're going to do later, or you can just use electric forces. So let's suppose that there is just electric fields. Can you have an object with a given mass, say 5 grams, be suspended on a given surface if there's an electric field? Yes. So let's show you the example. So let's say that you have a surface here. Right? And you have a mass of 5 grams that you want to make sure is suspended without any sort of motion above the surface. All right? What should be the electric field in the region? That's the question. Right? So if you have an object, and I'm going to say that it has 5 grams and also a charge, so mass of 5 grams. So you can ignore gravity now. You cannot ignore because it has 5 grams there. And it has a charge of, say, 20 microcoulombs. How can you, or what should be the electric field in this region? It's a problem like that in the textbook. Look, what you need to do is you need to think about the forces acting in this object. One of them is the force of gravity, the weight. So if you want this object to be in equilibrium, there needs to be a force acting upwards. And what force will that be? The electric force. So this has to be in equilibrium with this. In other words, the electric force has to be equal to the gravitational force. Now we know that the force due to gravity is mg. What's g? 9.8 meters per second squared. And what's the electric force? Let's write it here. The electric force is EQ. Right? That's the equation we're going to use that. Because we're going to find the value of the electric field. So this becomes EQ equals to mg. Now, if the electric force is going upwards, That means if that's a positive charge, that's positive, right? The electric field also has to go upwards. Now I can find the electric field by using that. E times Q, 20 microcoulombs is 20 times 10 to the negative 6. Equals to the mass, 5 grams. Okay. 1,000 grams is 1 kilogram. So 5 times 10 to the negative 3 kilograms. M times G. And then you are. E will be 1, 4, 2.4 approximately times 10 to the 3 newtons per coulomb. So that's the magnitude of the electric field. What's the direction? Upwards. So the electric field will be 2.4 times 10 to the 3 newtons per coulomb in the positive y direction. Okay, so what have we learned on this? Before you guys start going, please, I have to take attendance, okay? Or double check it. First of all, you can use the electric field in other type of situations that we didn't do before, right? Interactions between matter and electric fields. Next class, we're going to start with another type of interaction and charges in motion, by the way. Electric fields can actually be very large. This is actually 2,400 newtons per coulomb. So that's another important property of electric fields. They can be very large. While we found with forces, they were very tiny, especially if the charges were small. So that's how we're gonna finish it today. I don't know if you guys have any questions, but honestly, what we did today, you can start doing the first 4 to 5 problems on the assignment. The assignment can be found in Canvas. If you go to modules, all right. Okay, let's see. So are there any questions?
I don't have any questions about the material, but the WebAssign isn't working for me. Like, I have the class on my dashboard, but every time I click on it, it goes to my previous physics class. So I'm not able.
You have to register with the code provided in the syllabus.
I did. It's in my dashboard. So I know it's there. I'm not able to access the actual course materials for the class.
Did you use the code I posted though?
Yeah, I did.
You did?
Yeah.
What's your name?
Ramya Radhakrishnan.
Ramya Radhakrishnan?
Mm-hmm.
Yeah, you are in the class. You may have to look at one of the tabs and go to, like, just double check when you go to WebAssign. Just make sure you click. It might be there. I don't know how you guys look at it, but I see you in the list though, in WebAssign.
Yeah. Okay. I'll just
go back
trying
and see if you can, because sometimes you just have to change the book or the course or the code. So you are already registered. Yes.
Okay. Thank you.
Just double check that.
I'll try again.
Yeah, just double check and then send me an email. All right.
Okay.
Let me just don't go yet. I just have to double check. Some of you guys were not here. All right.